Now let's take up another theorem, which is actually a generalization of Peterson's one-factor theorem. The Peterson theorem stated that every cubic graph without cut edges has a one factor. But now here the theorem states that every k regular graph of even order that has k minus 1, that is k minus 1 edge connected, that again has a one factor. Now here in fact if we put k equal to 3, that is a 3 regular graph, which is in fact a cubic graph, then it must be at least 2 edge connected, then it will have a one factor. So this is a sort of generalization of Peterson's theorem. Now let's take up the proof of this theorem as well. So let's begin the proof. So let G be a k regular graph, that is k minus 1 edge connected, and let S be a subset of vertex set of G, and let O1, O2, so on, OR be the list of all odd components of G minus S. And we want to show that this graph has a one factor. We show G has a one factor, and for this we show the number of odd components in G minus S, which is in fact taken to be equal to R here. We shall show this is less or equal to order of S for all S contained in vertex set of G. And then we shall again use the Tutte's one-factor theorem to conclude the proof of this theorem. Now here again let us define these quantities. So let this order of OI is equal to NI, and let us define this MI is equal to number of edges having both ends in OI, and define this KI is equal to number of edges having one end in OI, and the other end in S. Again, let's make some construction here as we have done in the previous theorem. Exactly, we have the same construction again. So we have this, suppose we have this odd component here, which is denoted by the component OI, and there are some vertices here, and so on. Now there may be adjacencies within this OI, and there may be adjacencies outside this OI or from OI to some vertex set of S like this. And assuming that the number of adjacencies from OI to S is equal to KI, and the number of adjacencies within OI is equal to MI, and order of OI is equal to NI. So this is our set S. Now first of all, since the graph is k minus 1 edge connected, so since G is k minus 1 edge connected, we have this Ki is greater than or equal to k minus 1. The reason for this thing is, let's look at the definition of Ki first. Ki is the number of edges from OI to S, and the graph being k minus 1 edge connected means that the removal of less than k minus 1 edges from the graph G does not leave the graph disconnected. So we require at least k minus 1 edges to remove from the graph so that the graph becomes disconnected. Now if this Ki is not, suppose if we choose otherwise, if this Ki is less than, suppose k minus 1, that means then if we remove all those Ki edges from here, it will leave the component OI disconnected from the graph G, and that will be contradiction to the fact that the graph G is k minus 1 edge connected. So that means this Ki, that is the number of edges from OI to S, must be at least equal to k minus 1. Moreover, we have, now let's compute the vertex degree of this OI, the total vertex degree of OI. Let's compute this number. This V belongs to vertex set of OI degree of V. Now as we have done it in the previous theorem, this is equal to twice the number of edges within OI, then plus the number of edges from OI to S, which is equal to Ki. So in fact this is equal to twice Mi plus Ki. So this implies this Ki is equal to summation V belongs to vertex set of OI degree of V minus twice mi. Now let's look at what is this summation v belongs to order of oi degree of v. Now as we know that the graph G is a k regular graph, so every vertex has degree k. So in particular every vertex in oi has degree equal to k. So therefore this is equal to k times ni minus twice mi. Now let's look into this equation. So we have got the equation ki is equal to kni minus twice mi. Now here in this situation, here kni is odd. Here ni is odd. And because this ni is the order of an odd component, so ni must be odd. Now if this k is odd, then this number becomes odd number minus even number. So this becomes ki is odd. And if k is even, then k into ni is even, so even minus even is even, so ki is even. So therefore what we are obtaining here is that if k is odd, then ki is odd, and if k is even, then ki is even. So this means that k and ki have the same parity. So hence, if k is odd, then ki is also odd, and if k is even, then ki is also even. Therefore, k and ki have same parity, and parity here means the property of an integer being even or odd. Now we have the situation that ki and k have the same parity, and we have the equation inequality ki is greater than or equal to k minus 1. So therefore the ki, when it is given to be greater than or equal to k minus 1, but k and ki has the same property parity, therefore ki must be greater than or equal to k. So what is the reason for this thing? We already have this ki is greater than or equal to k minus 1. Now the one situation is it possible that ki is equal to k minus 1? Now if ki is equal to k minus 1, if ki is odd, then k minus 1 is odd, so therefore k must be even. But since ki and k have the same parity, therefore if ki is odd, then ki has to be odd. And odd is equal to odd minus 1 is not possible. And at the same time, if ki is even, then k is even. Then here from this equation we get even is equal to even minus 1, which is again not possible. So therefore this is not possible. Ki is not equal to k minus 1. So therefore when ki is not equal to k minus 1, that means ki is bigger than k minus 1. That is ki is greater than or equal to k. So this is an important equation for the next part of the proof. So now let's take up the sum of this equation when I runs from 1 to r. So this implies summation I runs from 1 to r k. This is less or equal to summation I runs from 1 to r ki. So this equation gives us r times k is less or equal to summation I runs from 1 to r ki. So let's keep this equation in here. Now next consider, let's calculate this quantity summation v belongs to s degree of v. Now this will be in fact equal to k times the order of s, because every vertex in the graph G is having degree k, so therefore every vertex in S has degree k, so therefore this sum of vertices of sum of degrees of all vertices in S must be equal to k times the order of S. Now let's again compute it in terms of the degrees that are within S and the degrees that are towards OIs and the degrees that are outside of S and outside OIs. Now first of all, this will be equal to, suppose let's write the equality here for time being. This is equal to twice the number of edges that are within S, then plus, because every edge contributes 2 to the total degree, plus the number of edges that are from S to ki. So therefore that is equal to k1, the number of edges that are from S to O1, then plus the number of edges that are from S to O2, then plus so on, then plus the number of edges that are from O to S to OR. So the total vertex degree of S is, first of all, the total number of edges within S. They will contribute 2 to the vertex degree, so that is twice the order of edge set of S, then plus. There may be some edges from S to OI, so that is equal to edges from S to O1, that is K1, edges from S to O2, that is K2 in number, plus so on, plus KR, that is edges from O2, edges from S to OR. But then there can be some edges like this that start from the vertex of S towards some vertex of G, but that vertex need not be in OI. So therefore this number will be actually greater than or equal to the total number of, this will be greater or equal to the k times the order of S. So therefore here we must have greater than or equal to, because there may be some more edges from S to some vertex of G, but that vertex of G need not be in OI and that need not be in SO as well. So therefore from this equation what we obtain, so hence we have, let's consider this equation first of all. So we have this RK. Now this is less or equal to summation I from 1 to k. So this is summation I from 1 to r ki. But now this is itself less or equal to summation I from 1 to r ki plus some quantity, and that quantity we shall use here twice, e of s, twice the number of edges in within s. But now this quantity is here actually, and this is less or equal to k times the order of s. So from this inequality we obtain, this implies r times k is less or equal to k times order of s. So now cancelling k on both sides, this implies r is less or equal to order of s. But r was the number of odd components in G minus s. So this implies this k naught of G minus s is less or equal to order of s. And s was an arbitrary subset of V. So therefore we can write for all s contained in vertex set of G. So hence we have shown that for any set S contained in vertex set of G, the number of odd components in G minus S is less or equal to order of S. Hence Berta's theorem. Hence Berta's one factor theorem. G has a one factor. This completes the proof of this theorem.